Hello, hello, hello. So, so we are live. So, hello everyone. We are live. We are live. Nice. Just a second. We have stats. Stats. Just a second. Hmm, Okay. So, yes. Okay. Close. Of course, we are getting zero views as usual, but the stream is supposedly stable right now, which is good, hopefully. So, properties, but I don't have any properties. Okay, there's still some issue with this. It's okay then. So, hello everyone, we'll be starting with making our own Regex Parser today. That too in Golang. Why Golang? Because make making React from scratch was just to learn React how it works because I had to use that in my in my internship. So that's why. Other than that, I'm not so much interested into front end, but yes, nonetheless, it was very good experience to create React from scratch, something which I don't know how many developers use on daily basis. Okay, and then if we take a look here, okay, so we are streaming. Let me see how can I move and if I'm in the frame or not. Yes. So if I go here, a little bit like this. Okay. And then if I go here, 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 yes, it works now. So let's start with the blog post. Okay, so how to build a regex engine from scratch. We'll be following this. Now you all will be like, why I don't code it from scratch, building my own logic. Let's be honest, I'm not good at logic. I really despise DSA. I really hate it, but I like building stuff. So I follow these blog posts hoping I learn something. Like if you see in React Parser, okay. So if you can see that in React Parser, just a second. React from scratch. No need to do cd, we can do cat, and then we can do lib react dom. So if you can take a look at this file, we actually created, we actually did dfs. So if you do perform and you take a look at this function, we are actually doing dfs on a tree. We created a tree. And where did we create it? So to take a look into that, we can actually take a look at reconcile. Yes, so this is where we build it, right? This is where we build it. Nice. So we created a complete tree structure. We did depth first search on it. We rendered everything. We used create DOM and then everything like that. Then yes, it worked. We also initiated this thing right over here. So yeah, this worked, and to be honest, I'm very happy with this working. The reason being that technically, like I got to learn how DFS works, and this was not like a proper DFS. There were in a proper DFS, you actually first go through the child, and then there is a stack. But here we are doing recursion, so recursion actually makes a stack of its own. But then passing through sibling is also a different thing, and how we did that here was a little bit different from a common DFS algorithm. It is similar in the way the logic goes, but the code was a little bit different. But I got to learn some logic through this, so that's why I like building stuff rather than uh, doing DSL. So I'm hoping I'll be able to learn finite state machines by creating a regex engine from scratch. So let's go ahead with the article. In this article, we'll build a simple regular expression engine that will be able to use okay, these patterns right over here. Okay, okay. Pattern dot is used as literal instead of any character to check for availability of email addresses. So this is the description. If you see, but if you see, this is the description. We'll be building a simple regular expression engine, which can parse these expressions right over here. So I'll just add it to description. Okay, now we capitalize this. Okay, cool. So first we go through parsing, then we build the state machine, and then we go through matching the string. So I'm mostly interested in this part because I'll get to learn how to code finite state machines. But yeah, we have to go through parsing also, like how we are going to parse this. So on its own, a regex string is just that, a string. We need to transform it into something that has a structure, such as following. So we have this original regex string, and then we have the regex tokens. So generally, a parser divides a syntax, a grammar into its tokens. So this might be a token, this might be a token, sorry, and then 0 to 9 might be a token, and then these square brackets are also tokens. So repeat 1 till infinity, range a to b to z, a to b to z, and 0 to 9 comma underscore. Okay, and then we have literal at the rate, repeat 1 to infinity, range a to b to z, a to b to z, 0 to 9. Then we repeat 2 comma infinity, and then we do this. Okay, in this section we will go over the process of parsing a regex string into tokens. The core idea when it comes to parsing a regex string is simple. We will look for characters that have special meaning, such as asterisk, plus, question mark, parentheses, uh, square brackets, and braces, etc. And we will try to create tokens with the help of those characters. It will be more clear once we start writing code. Before getting into parsing algorithm, let's define some types and constants. So what am I going to do here is, what I can do is, of course, I can first of all write this main.go package main. Okay, do I require go.mod? I don't think so because we aren't installing any libraries. Let's go ahead with this currently. So import, and then func main, which returns nothing. So this is the skeleton of our go code. Of course, we can enable LSC on this. Nice, and then we can start making a token type. So of course we have token type as uint8. So type token type as uint8. Hmm. Hmm. Should we call it token type? Token underscore T would be very good, but as far as I know, Golang has some strict rules regarding the type, like the notations and syntax and how you capitalize words. So instead of typing type, I would prefer it having sort of like this. So token T. Then we have, of course, we are technically making an enum. So Go doesn't have enums by default. So we do this kind of thing. IOTA is nothing but you can say a counter which automatically increments. So it will start from 1, 2, 3, 4, 5, 6. So what we can do is const, and then what kind of tokens we have: group, bracket, or repeat literal, group uncaptured. So group, and then we have token T, and then iota. Yes, so which is equal to iota. And if I go to definition, see, so const iota is equal to 0. Iota is a pre-declared identifier representing the untyped integer or real number of the current constant specification in a usually parenthesized constant declaration. It is 0 index. So here currently iota is 0, but if I do this and then change it to bracket, if I'm not wrong, yes, then it should be 1. It will be 1 here, but yeah, this is after we run the go code, you can will print this out once. So we have or repeat literal, group uncaptured, or repeat literal, and okay, and we have group uncaptured. Okay, and then there's a very nice command, if I not know, go format dash dash s dash w. Yeah, so it formats the code. And then we have group uncaptured, token type iota iota iota. Then we have a token struct. So we have, so let us define all the types above. Then we have a type token, which is a struct which contains a token type and value. We can have type token T and value, which is okay, which is an interface. Damn. So instead of using interface, we can technically use this. So what this does is, if I'm not wrong, just a second. Okay, so we need to be flexible with the type. Okay, of course we need to be flexible with the type. Why the hell it isn't showing anything? Okay. Hmm. Okay, but as far as I know, Go aliases any this, so any is alias of interface. So everything is an interface in Go. Like that's the kind of approach they have taken. But yes, so what is so okay? It's line number 5, expected closing bracket. Oh, sorry. So type is already a keyword in Golang. So we have to call it token type. We can also call that as t. This will work. Yes, so this works. And now yes, you can see any is equivalent to interface. So yeah, we will just call it any, uh, and then move ahead. Then we have parse context. So the index of the character we are processing in the registering. So we have type, parse context struct, and then we have a cursor position. So we have position, and then we have tokens. So we have position in, and then we have tokens, which is of type, which is of type slice of a token. So, so token type is self-explanatory. Parse context isn't. So the index of the character we are processing in the registering. So index of character, so it is context of current parsing with index of character and array slash slice of tokens with current index of. So if we do this here, yes, context of, yeah, correct, correct, correct. Okay, so we have this. Cool. And then what else do we need? So we have tokens. Okay, so in this section, okay, and let's define some types and constants. First, it's just okay. So first, it's just a type alias for character type. Yeah, character is 8 bit ends. Yes, it is 8 bits. No, it is 8 bits, right? Yes, it is. If I'm not wrong. Yes, it is 8 bit ends. So it is 1 byte. So 8 bit ends. It's usually a type alias for character type. Okay. Constants for specifying the type of tokens we are working with. Think enums. So yeah, this is an enum. And the main token struct, it has a type and a value which can be anything depend on the given type. And then we have parse context, which will help us to keep track of our positions and will hold the tokens parsed so far. Okay, so technically it is very similar to writing a parser for a language. You can technically make parser for anything if you have a well defined grammar, syntax for that language. So first of all, to show you guys, we can print these things right over here. Okay, so println, hopefully this is a thing. Fuck dot print, yes, println is a thing. And then we have group, and then we have bracket, and then we have or. So three examples are enough. We will organize imports, and then we will run this. Okay, cool. And then we can go and run this. So it should print 0 1 2 or 1 2 something like that. Yeah, 0 1 2. So iota auto increments itself if it is used uh, around this constant type. Cool. So now next is our parsing algorithm. Okay, so we call a function the function parse, which will return a parse context. Of course, it initiates the parse context with 0 and an empty slice of token of type token, and then it iterates over the string, processes the string, and increments the position and returns the context. Hmm. Okay, makes sense. So we'll put this function from parse. It takes a regex string. Regex is a keyword. Yeah. Okay, so regex string, and then it will return parse context. Yes, and a pointer to that. In fact, so first we create a context which is equal to a parse context. Okay, technically we don't need to fill this. It will automatically take the zero values by default, so position will be zero and tokens will be empty, so I don't need to define that anything here. And you can see that if I print this, so if I do fmt dot print context, printer in context, and then if I return context, but regex is unused, so we can do this and do regex, so regex, and then we can go to main, so and then we can call here parts, and then it returns something. So for it to return nothing, we do this. Yes, and then I go and then so no new variables on the left hand side of. Okay, so by default this is defined somewhere or the other, so we just. Yes, and if you can see here, we have 0 and empty slice. So by default, every what do you say, primitive type in Golang is instantiated, or yes, it's instantiated with its default 0 value. So let us remove this, and for position less than length of regex, so for less than length of regex, process regex comma context, so process regex, and we do position increment. So now we also make a function process, which again takes in a string, and I don't know what it does, but it takes in a context also. Okay, since we are calling this internally and we will not call it from external code, this function process, we can just directly pass in a context here as an argument. Okay, so we have a context, and then of course we have to pass in a context here too, so that is of type pass. Yeah, we loop through each character and processes until we reach to the end of the regex string. Next, let's take a look at process method. It's a bit more involved, so let's take it step by step. So yes, we do have this. Then we take in a character from the position. If the character is this, we do this. If is but I wonder if we can use switch statements here, which we actually can. So how do they work? Switch statements. So we have C character is equal to regex at the current position, and then we call switch on ch, and then we do case. We have cases. We have cases of first of all we have cases of a parenthesis. Okay, then we can do paste. So we have a opening parenthesis, we have an opening square braces, we have a pipe, we have asterisk, question mark or addition. So we have these three right over here. So what we can do is 1 2 3 4 5 6 7, and then we have a default thing. So 1 2 3 4 5 6 7, and we have a default. Okay, so do we need to break case in Golang switch? Okay, except that Go only runs the selected cases, not all the cases that follow. So yeah, this is the best part. So, and this is what I suspected in Golang. So if you actually do this, right? Okay, I don't know why this is happening like this, but if you actually do this and you run it, so Go runs on Linux, right? And then it doesn't execute anything despite it not having any break statements. That is because okay, and then can we do multiple matches in single case Golang switch? So okay, multiple value cases. Yeah, we do have multiple value cases, which is nice. We have multiple value cases. Good. So that's why we search for syntax so that the things are easier. We don't have to use spike. We don't have to use equal to. We don't have to use else if. Yeah. So this is easier, right? Why do we have to do all this stuff when we can do it using switch statements? So first we'll take a look if we find a opening parentheses group context. Okay, so we again have a parse context, and but now this time it is a group context. We are grouping stuff. So we create a new parse context. So it is having a smaller regex string into a bigger one. So we create separate context for passing that, for parsing that, not passing that, parsing that. So yes, we have a group context. Okay, cool. And then so we had seven, but we had three in one, so we can remove the two, and giving us five. I'll just change them quickly. So I replace this with opening braces, opening brackets. Then we have a pipe. So we have a pipe, and then we have an opening braces. Cool, but before that we do have the asterisk. We do have a question mark. We do have an addition sign over here. So we do have these, and then we have braces. Sorry, so what we have is an opening brace. So what we need to do is group context is equal to again we need parse context. Okay, we need a parse context, and it will be, of course it will be initialized as a 0 thing, but here if you can see we do require the context dot position and not the zero value. So what we can do is we can just pass in position as context dot position. We won't pass the tokens since it is already empty. Yeah, and then we have parse group. Okay, and then we have parse group, Shouldn't it be process group? Uh, because we even call process inside this parse, we should call this process group instead of parsing a group. And then the parse, okay, so the parse group will call process group. Let's see. So we have context.tokens is equal to append context.tokens comma, we take this go. Okay. What the so value is okay, makes sense. So we parse the group. What do we parse in group? Okay, so we parse regex and then we parse uh, group context. After doing this, after doing this, after parsing the group, we do need to update the token we have encountered. So what we can do is ctx.tokens is equal to append ctx.tokens comma the value we need to update that with. So of course we need to call token, okay, and then this, okay, so we can fill that automatically using the LSP. So we have a type and the type is group and the value is, so here is the point. So now the value is it should be group context dot tokens. Hopefully this should be the value. So yes, this should be the value. Cool. So now we have this. Okay, and then if we have found a bracket, parse bracket. Okay, so we do parse bracket, and we have bracket, and then we have a pipe, so we have to parse or, of course it is or, and then we have sorry, parse or, and then we have repeat and repeat specified, repeat and repeat specified. So we have repeat and repeat specified, and then we have a default thing. So default is unhandled, so we just take and create a token of type literal. Okay, so we don't have unhandled one, right? So we make it a literal, we put the value as character and append it. So what we can do here is we can actually borrow the code from here, take it to here, paste it, instead of group, that is of type literal, yes, and then instead of this the value is character. So we have done this. As mentioned earlier, we are trying to match characters. We recognize and use them to parse tokens. If the group is a character, opening parenthesis, the opening parenthesis, we know we are dealing with a group. Thus, we try to parse the next couple of character as a group. If it is a opening bracket, we know that it's a bracket expression, so we proceed accordingly. If the character is a vertical pipe, that's an OR expression. The characters asterisk, plus and question mark all represent repetition. I know that question mark means optional, but it in terms of repetition it simply means that the character repeats at most once. Makes sense. Curly braces specify repetition as well. In fact, the previous repetitions options can all be specified using braces. A star is equal to a0, a plus is equal to a1, and a question mark is equal to a0 comma 1. If the character did not match with anything, we consider it as a literal. Please keep in mind that this is a simplified implementation. There is a lot of cases to consider when it comes to parsing regular expressions. For instance, one is a literal, but depending on the context, it can actually be a part of back reference. So there's something very good about regexes, that you can capture a group in the first part of regex and then actually reference that ahead by using this syntax right over here. So that refers to first capture group. A simplified algorithm also does not consider the escape characters, which means backslash a is considered as a concatenation of two literals backslash and a. Okay. Next, we'll examine each function defined in above snippet. Let's start with parsing of group expressions. So now we parse group expressions. And since group are nothing but smaller regexes and bigger regexes, we can actually take a look at this. So we can actually call process here. Hmm. Get the how are we going to get this? Hmm. Okay. So we go here. We call this. Call this. So it is a string and it is parse text. Okay. And then we have ctx dot position is equal to 1, increment position for getting for character after this. And then for regex ctx dot position not equal to, we follow a loop, we process regex string. Okay, we don't need to define that. And then group context. So okay, so okay, we cannot. No, yes, it is group context. So context text. Okay, and then we have ctf dot post plus 52. So we have this, which is nice. We process each character like we did in the parse method until we encounter the closing parenthesis. We will not cover the error handling in this tutorial, so we are simply not checking if the index is still within bounds. It will panic anyway. Oh, fuck. Okay. And if ctx dot position is equal to len of render, we dot returns an error. Print len. Oh yes. Okay. So we process each character like we did in the parse method until we encounter the closing parenthesis. We'll not cover the error handling in this tutorial, so we're simply not checking the index is still within the bounds. It will panic anyway. Okay, what about the extra code around parse group in the process function? What happens there? Here's the snippet. Okay, fuck you. We create a new context specific to each group. Of course, the top level context object. Once we are done passing the group, we'll bundle all that pass token into a new token of type group and append it to the global token list. I mean, let's now see how we can parse bracket expressions. This is whole function, but we'll cover it step by step. Ah, damn. So this is interesting. So parsing a bracket is difficult because parsing a group is like parsing a regex string. We can call it again the process function, but here we have to actually handle stuff. So yeah, we get past the bracket. We create a literal a slice of string, which are literals. Why is it a slice? Okay, for regex not equal to this, we get the position, we get the character. If character is equal to minus dash, next is equal to character, and then we have len of literals minus one. Okay, len of literals minus one. The fuck is going on? So it is a fucking thing with strings, and then if that has a dash, but dash cannot be at starting. So if dash is at starting, this will throw error because that would be 0 minus 1, that would be minus 1, and then we have will be reference will be what do we say, will be taking the value at the index of minus 1, which will throw an error. So yeah, literal is len minus 1 is equal to error. So we print previous and next, else append literals. Okay, so let us assume it is not this shit right over here. Then what that is this. So if literal is equal to append, so we convert that into a string. Can we convert it directly? Hopefully yes. But then here this. Why can't we make this a fucking string? Oh sorry, why can't we make this a fucking character type? There's something I'm missing. Okay, so literal set is equal to map movement bool. Okay, so it map and this is boolean equal 0 1 I plus plus is equal to true. Literal set is I is equal to true. But then the range of literal. Okay. That's why we make it a string. We have two close numbers. If we don't have a dash, we have a contiguous number. So 10 is 10, not 120. It makes sense. That's why we need that to be a string. Hmm. Okay. Hmm. Okay. Line up and paste it. Okay. So increment of the character after this. Okay, so we have this. Many people could have that. Why is this render? Regex. Regex. Okay. Okay. So we have, of course, we take the character. Okay, so we have to take the character, take the character. Cool. What is wrong with this guy? Okay. Then we take the character, we take variable drill, real drills. We are not using make, right? String. So this is a string. So we have an array of string, and then we loop over the characters. Sorry. So if we encounter a minus or a dash, so we first check this here, and then if ch is equal to dash, of course we call else. So if it is a dash, that means we have two different literals, and then we combine them into a single string. So we have a next and a previous string. So we have next, which is equal to regex ctx dot pose plus 1. And then we have previous, which is equal to minus 1. Okay, so we have two bits. And no, so the previous one is the literals len of literals minus 1 of 0. So we have literals len of literal minus 1 of 0. Okay, but then minus 1 indexing in Golang, do we have that? I don't think so we have that convenience available to us. Okay, we look at the stats. Okay, nice. The stream is running comfortably. So we have a boolean. Okay. Okay. So the previous one is not previous character in the regex string, but it is the previous literal we stored. So the previous literal we stored, and then we change the previous literal we stored with a string which removes the minus and concatenates both of them. So what are we doing is we are doing this v f closing yang paste we are doing is equal to dot string f we have percent c comma previous comma next okay and then we have, why do we have a zero here okay and then consume the next character this one and if it doesn't have a dash we can directly append the literal like this by converting it into a string okay so we do literal literals is equal to append literal comma string ch yes and then we increase the position nice but we don't process this grab anymore okay and then we have a little set okay and we create a fucking hash map out of those literals and how do we do that okay, so first let me make a literal set is it a literal set okay it is a literal set okay and then we have map unit bull so we have we have map uint it which which has a bool okay and it is a map so we instantiate it with 00 values that means it is empty map so I guess the zero value for a map is nil but let us see so we loop over the literals we since it is a string we take the literal l take its first character and we loop over to the last character and set it to be true literal set to be true okay now I get it so suppose we have a square bracket and inside that we have a dash I so it will take the a the first character it will take the I the last character and it will then simply set everything in between a and I to be true it doesn't make sense but because it is just 10 index it's just 10 index just 10 index so what we do what if we have a dash I dash o so a dash I dash o so we have something like a dash I dash o something like o something like that ayo ayo so we will have a okay a will be pushed down to the literals then we will have a dash so we take the I we take the a and then we make it ai and then we increment the position twice so now we are on so it was next right then we have a dash the next one is o so we take the previous literal and the zeroth index is still a and then we take on the last element of literal and replace it with A and O. So AO, and then we have AO. So this will return a literal list with AO. Now, if we have AO here, AO, we have a literal set AO. We have a range like this. L of 0 is A, L of LL minus 1 is O. So for I equal to A, the Unix, the ASCII value of A, to the value of O, ASCII value of O, everything in between should be set to true. So it is technically what I said. So it takes the range A to O, even if it has an I in between, it takes A to O, and then everything in between, it marks it as true so that we can search through that later. So for L in literals, there is no this. So for for I equals to L of 0 and I less than L less than equal to or less than equal to L of len of L minus 1 I plus plus. Hopefully this is it. So yes, that is it. And then we set it to be 2. So we set literal set of I to be 2. Okay, makes sense. Then we have, so then we append a token into the context, um, and the value of that token is this literal set. Okay, so we append it, so we append it, so we take ctx dot tokens, which is equal to append ctx dot tokens comma a token type. Yes, a token type, and we just fill this. It has a type and a value, and the type is literal. No, it is a bracket type. Okay, makes sense. Bracket, and then we have literal set. Similar to the way we pass the group expression, we go through each character till we reach the closing bracket. This, for each character, we check if it is a dash because that's the range indicator. Example A to Z, K to Z, and 2 to 8. When it is indeed the range indicator, we take the next character from the regex string and the previous character from the list of literals. That is the last character in that list. Then we save it back to the list as two characters together. We could choose a different way of saving past literals, but I find this to be simple and easy to understand. If it's not the range indicator, we consider it a single literal and save it to the list. Move on to the next character. Literals list contains both literals and ranges, but those many contain duplicates. Consider the following regex A2M and E2S. There is a clear overlap between the ranges. We go over the save values and each literal to literal set. By definition, sets do not contain duplicates, so that gets the job done. Since we are implementing this in Go, we are using a map because there is no natively provided sets in Golang, and installing a library just for a set is unnecessary. Makes sense. Add all the characters between first and last characters of the save value. In the string literals, this will only add the literal itself. Example, B will only add B. In ranges, it will add everything from the first character to the last character inclusive. Example, AD will add ABCD. Finally, once we have all duplicates removed, we save the bracket token to our list of tokens. Next in the line is parse or, which is able to parse alternations. So we have or, and here we take or. Okay, cool. So before we do all this, so we'll take a pause here, not a streaming pause, but we'll search basic regex syntax. Okay, so we do have a cheat sheet by MD and WebDocs. Let us go through that. Okay, so it's utterly useless and I hate it because they are not in a good format. We can go through the Wikipedia. Okay, describe regular languages using this mathematical notation called regular events. Okay, and of course we have a state machine translating the clean star. A star means zero or more of S. So if we have Q, we have an epsilon, we have okay. So we have a basic concept here, and of course this is also shit. But since it is Wikipedia, we need to copy clean link and we will add it to our description. Yes. Okay. Okay. And then let us find for a better quick start. Okay. Hopefully we get something interactive that will help me learn. Fuck. Why don't we have some easy practical guide to regex? Okay, with regex. Exact match character set. Okay, let's go through this. So a regular expression is nothing but a sequence of characters that match a pattern. Besides using literal characters like ABC, there are some meta characters and so on which have some special purposes. There are also features like character classes which can help you simplify your regular expressions. Before writing any regex, you will need to learn about all the basic cases and edge cases for the pattern you are looking for. For instance, if you are matching hello world, do you want the line to start with hello or can it start with anything? Do you want exactly one space between hello and world or there can be more? Can other characters come after world or should the end line end there? Do you care about case sensitivity and so on? Make sense? These are the kind of questions you must have asked to before you sit down to write regex. Exact match. The most basic form of regex involves a matching a sequence of characters in a similar way that you can do with Control F in a text editor. Okay, fuck this Control F. We have a character set. So a regex character sets allow you to match any one character from a group of characters. The group is surrounded by a square bracket. So the group is surrounded by a square bracket. What the fuck? For example, T square bracket AH square bracket close I matches tie T. Here T and I are fixed, but between them can occur A or H. But it could be thigh also, right? Or what the fuck? Okay. So we can also call a regex testing tool, something like that. Okay, regex 101. Nice. So insert your regular expression. So we have ta he, and then we have that. Okay, then we have tie, we have thi, we have this, we have tamp, we have thigh. Okay, thigh is not getting matched. The fuck? The fuck. Okay, and then we can also have bithai. Okay, so bithai. Okay, so that's how this works. Nice. So okay, so this will match either of them, not every one, but either of them. Okay. Match ranges and rejects. It's like a range operator. Some valid ranges are shown below. Okay, so you can specify partial ranges such as B to E. So can I do this over here? So if I go to this, I do this, and then we have tie, tie, T, tie, tie, uh, T, T also doesn't match. Damn. What else can we have? Hmm, we have, and then we have C, we have D, we have T A I tie, T B at B, T C at C, T at D, T at tie, T F at P, we have T, we have T, we have TII, but it doesn't match. Okay, so now we got how to match this ranges. Okay, you are not limited to specify only one range inside a character set. You can use multiple ranges and also combine them with any other additional character ranges here, or semicolon. Fuck. So everything inside braces is either range or an or. Okay. Match any character not in the set. Okay. If you prefix the set with this inverse operation will be performed. For example, okay, so upper cases. Okay. So here I can do it. So I don't want anything from A to Z or 0 to 9. Hello. Okay. That Z isn't. Yeah, what is this? So we have hello world. But if I do this like this, and if I do this like that, and if I do okay, so it only matches to uh, small lowercase letters, but that is individually, not that too, not in a group. It is one at a time. Okay. Okay. And so we have this. We have character classes. While writing regex, you'll need to match certain groups such as digit, q, offer, and multiple times in the same expression as well. So, for example, how would you match a pattern like letter, digit, letter? Yeah. What you have learned up till now, you can come up with, of course, of course. This works, but you can see how expression can get quite messy as the pattern length gets bigger. Makes sense. To make the expression simpler, classes have been assigned to well-defined character groups such as digits. The following table shows these classes and their equivalent expressions for character set. So we have digits. Okay. So if I do this, if I paste this, we have A0, A0. No, but this isn't getting recognized. So A0, A0. Okay, this does get recognized. Okay. Okay. Ah, okay. So we are also learning about regex right now. Damn. So I knew certain basics things, but yes. Okay. So we were here. So we have word character, which means this. Anything except new line makes sense. Non-word characters, just put a backslash, w, and then a not in front of it. Digits, non-digits, of course, spaces, tab, and new lines, non-space character, white space characters. Character classes are quite handy and make your expressions much cleaner. We will use them extensively throughout this tutorial, so you can use this table as well as table as a reference point. Okay. W is word, capital is not word, S is space, capital is not space, D is digit, capital D is not digit. So yeah, and dot is anything except new line. For example, T dot dot matches anything that starts with T and any two character afterwards. This may remind you of the sequel like operator, which would use T percentage to accomplish the same thing. Okay. Quantifiers. So the word pattern and repetition go hand in hand. If you want to match a three-digit number, you can use backslash d three times. But what if you need to match 11 digits? You could write backslash d 11 times, but a general rule of thumb while writing regex or just doing any kind of programming is that if you find yourself repeating something more than twice, you are probably unaware of some feature. In regex, you can use quantifiers for this purpose. For match 11 digits, you can simply write the expression backslash d 11. Okay, so if I want to match a phone number, can I do this? So that doesn't matter. But if I write a phone number, okay, so only this part matches. Okay, so only this part matches. Nice. But what if I wrap it inside a square parenthesis? This work. It doesn't work. It takes it individually. Hmm, what if I do this? Okay, it does match that. Two, two. Okay, so we have quantifiers which repeats the pattern. The table below lists the quantifier you can use in regex. 0 or more, 0 or 1 or more, exactly n times or more, and 2m times inclusive. Okay. In this example, the expression can backslash s plus right. So we have either one space or more space. Matches can followed by one or more white spaces followed by right. You can see can right is not matched as that means one space needs to match. This is also when you can write when you are searching through text which is not trimmed. Can you guess what match to this 0 or 1? So it matches to this, the can write one, or a normal can write which we I guess don't have here. Nice. Capture groups. So now we have capture groups. The capture groups are sub expression inclusion parentheses. You can have any number of capture groups and even nested capture groups. The expression the braces 2 matches the twice. But without a capture group, the expression would match the followed by two spaces. Okay, so this will be the pattern to match, and that will be called twice. The followed by two spaces. As the quantifier will be applied on the space character and not the as a group. So this is the power. This is capture. Okay, you can match any pattern inside a capture group as you would with any other valid regex. Here is okay. So what if I do this? What if I want to find duplication next to each other. So what if I create a group with backslash w. Then I do this. Okay. So this is my story. But I want this to be done twice. Does this make any sense? So if I write the hello world, comma the no. So we can match a word twice. So we have th. And that too it doesn't specify. So if we do this, but we can do this also, right? It is either t or t. Doesn't work like that, but it is supposed to work like that, right? So what does this matches to? It matches to the right, and then we have the qualifier. Okay, but then what if I put a space here? Okay, okay. Okay. Now it matches them twice. So any word which I keep here should match it twice. Then okay, makes sense. Okay, matches is s plus twice. If it is s is followed by one or more spaces twice. So is okay. How to use logical or in regex? This is good, bad, or sweet. This is good, bad, or sweet. This is good, bad, or sweet. This is good, bad, and sweet. Okay, which is a capture group is attributed to this is, but if it is not inside the okay. How to reference capture groups? So this is the first capture group. Okay, this is this power. This is this power. This is this power. Okay, how to name capture groups? You can name your capture groups with syntax. Damn, I can name capture groups. Fuck. What do I want to name it? Okay, so I can name. So I have named this lang, which takes in a word which should occur once or more than once. Okay, any word which occurs once or more than once, and see if it occurs more than once is the best. But so any c okay. So anything which contains how many words? There's one or more, right? So this plus okay. Any will match any word character or plus character one or more times. Okay, makes sense. So C++ is the best, but C++ can be hard. Okay, Java is the best, but Java is ugly. Python is the best, but Python is slow. Okay, makes sense. How to use regex with command line tools? Recursive regex search with grep. The fuck is wrong with this? Okay, code rush with flag format. I will show you the solution to a challenge I created to a CTF competition at my university. The file attached to the challenge is a zip file that contains multiple levels of directories and a lot of file in it. The name of the competition was Code Rush with flag format. Code Rush flag is here. You have to search for pattern Code Rush in which will match the flag format Code Rush any character here. Unzip the file with unzip into the cdr zip z color. Okay, dash color we can provide a fucking color. Okay, and dash r recursive, we call it recursively, and enables recursive search. You can learn more about them. Okay, so we do have a color. This is a flag you were looking for. Nice. Substitution with sed. Okay, sed does a substitution pattern and replace g. Okay, here's the option G is specified to replace all occurrences. Some other useful options are dashing to separate the default behavior of printing all lines, and using P instead of G to print only the lines which are affected by the regex. Okay, so hello rand characters were 56 rand characters. Our task is replacing hello number with hello number only in the lines where grep is present. Okay, so the grep is present. So we are searching for pattern hello. Okay, and then 0 to 9 plus more characters which will match hello followed by 1 or more digits, and all the digits are captured. Then our replacement will be hello underscore and 1 is reference the capture group containing the digits. Okay, makes sense. One way to accomplish that would be using grep to grab the lines which have grep present, then performing the replacement with said. But then why are we even picking numbers? We can just directly replace hello with hello. The fuck? Why do we have to change the number? Okay, okay. This is only to the lines where pattern is present. So use slash pattern. Oh, okay, 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 okay. But then again, I can use grep and pipette. So yeah. So there is a look behind. So we already know how to satisfy the first condition. So let's say you want to match the word Linux, but you have two conditions. The word GNU must occur before Linux occurs. If a line contains Linux but doesn't have GNU before it, we want to discard that line. We want to match only Linux and nothing else. Okay, we already know how to satisfy the first condition. We can do this. We'll match GNU followed by the number of characters. Then we finally match the word Linux. This will match all the GNU any character Linux. Okay, but how do we prevent matching GNU while still maintaining the first condition? That's where a positive look behind comes in. Then mark the capture because a positive look behind the fuck. No, I'm not doing this. Okay, I could have just grabbed the fuck out of that. Okay, and look ahead. Fuck you. Okay, okay, okay. Blah, blah, blah. Okay. Okay, okay, okay. So now we have good enough context about regexes. GG, and we have okay. So let us take a break now. We have a good context about regexes. We will continue in a while. Thank you. Hello, hello, hello. So we are back. So let us continue with our operation parse or. Okay, we have parse group, parse bracket. Now I can parse, func parse or, and then I can yank this and then paste this and yank this and paste this and yank this and paste this and yank. Okay, so now we have our just context, and then we must be having, okay, there is no LHS context. Okay. So LHS context is good past context, tokens, then get past this, get past this. We have RHS, both sides of the OR expressions. Hmm. Okay. And then we have CTF dot position of the right position. And then we okay. But then there is an issue, right? No, there isn't any issue because if it is a group, we don't have the global context. We have a group context. Nice, it's fucking smart, man. Parsing is very smart in this. So if you can see how we are doing parsing here, we are actually relying quite a lot on this context. And if this was not here, the parsing would have looked different. So if we are in a group, if we are in a group and we have a or operator here, so if we have the or the something like this, since this confines the context, the group confines the context, creates a new one. It automatically has a left and a right. What if I do this? Hello. Okay, so we have a context. It will encounter this right and left, and then this would be this would be considered as the left, and this would be considered as the right. Makes sense, yeah. So, okay, let's first go through this. So we have a RHS context, which is equal to parse. So here we make a parse context, which I shall fill it up with context corporation and empty tokens. So makes sense. Then we increment the position to get past that. So I'll just context dot pos plus plus. What is this? This is to do this stuff. So this is to, I really don't know what I, okay, so this, okay, so this is to do this. You know what would be the best part? So we do this, we end this, G. So we paste it here, we do this, increment position for character after this. Okay, we do this, we say no to highlighting. I really don't know how to type the numbers using touch typing, so that is quite difficult for me. And of course, the special characters you have right next to PL and M. Yeah. So we have the position, we increment the position, we increment the position, and then for the position and less than regex, and regex is not equal to this. Of course, of course, of course, we need this. So for HS dot everything equal to, so len of regex, yes, and then and RHX checks, no, so regex of RHS context dot pause is not equal to fucking bro, fucking bro. Yes, so this is it. We again process the regex, comma, the RHS context. Okay, then we increment the context, RHS context dot pause plus plus. Then we have a left side of the, okay, so we have a left side of the pipe and we have or, and we have a right side of an or. So we can define left to be equal to okay, group uncaptured, and then we have value is context dot tokens. Okay, we do have this. Then we take the position to be equal to RHS context position. Of course, we just jump that part. We jump that part in the context. So we have ctx dot pause is equal to RHS context dot pause, and then we also have a right side. But for right side, of course, we do this. We paste it here. We call it a right, and then we just do this RHS. RHS context dot tokens. Do this. We do this. We create a token type left and right. So we ctx dot tokens is equal to. But now, if you see, we are not appending it. We are not appending it. We are not appending it. Damn. So what we do is we create a token type with the fucking type of or, comma, to value of slice of token with right, comma, left. Nice. Left, comma, right. Sorry. Left, right, comma. Nice. So we have this. So the alternation of the operator has the following syntax: left and right, or left and right, meaning it has alteration between what is in the left hand side and what's on the right hand side. By the time we encounter this pipe symbol, we have already passed everything to the left of it. Now it's the time to pass everything to the right. It's almost the same code as parsing groups. We create a right hand side specific empty context and call and collect all the tokens into it. We do this until the end of the regex string or we face a closing parenthesis. Now that we are done parsing both sides, it's time to create the alteration token. The left side will contain all the tokens that were in original context object because it contains all the tokens we have passed so far. For the right hand side, we take all the tokens collected from the RHS context objects For both tokens, we use group uncaptured as the type. It's simply a type that create a type created to indicate a bundle of tokens. We update the position of the original context. We create the alternation token and add it to the original context. One important thing is that we do not keep the old tokens in the original context, as they are already contained in the alteration token. Of course, they're already contained in the left. Now let's look at repetitions. So we have variable min max. Okay, okay, okay. Okay, 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 okay. Okay. Ah. So, so what do we have is we have parse. Okay, so we have func parse repetition. If I'm not wrong, it is repeat. We do this, and then we have ch regex of context dot position. What do we have here is we do this the fuck. We do this, yank it, paste it. Now we have the context, and then we take the position. We have var main min max int. We have var min max int. Then we have a switch ch. Then we have a fucking case. Cases of asterisk, question mark, and plus sign. Asterisk. Question mark and plus sign, and then we have a default which fmp dot print ln to do handle error unidentified repetition token. Okay, now if it is a star, we have min equal to 0, and then max is equal to repeat infinity. What the fuck is repeat infinity? That is -1. Const repeat in int is equal to -1. -1. Okay, and if okay, then we have min is equal to 0 and max is equal to paste paste. We have 0 1 and 1 and infinity. 0 1 1 and infinity. So we have 0 1 1 and infinity. We need to grab the last token with the qualifier data so that we know what the min and max applied to. Okay, so we need to have the last token with this. The last token colon equal to, we have, okay, so I just do a zz and then dd, and then last token is equal to context dot tokens len of context dot tokens -1, and now we have that, and then we make the same thing, the same stuff. So we take this, we yank it, we paste it, we equal to this, okay. So there is that, then we equals that 2. We equal that to a token we just created right now with a type of okay. So we have, what are the types? The types are, we have a repeat type here, repeat. So we have a repeat type. Where is it? Here is it. So repeat. And then okay, we have a repeat type. We have a value. We have a value. Repeat payload. Then we have to repeat payload. We have to define repeat payload. We haven't defined it yet. We need to define repeat payload. Repeat payload has min, max, and a token. There's a min, max, and a token. Repeat payload. It has a min, which is min. It has a max, which is max. It has a token, which is last token. GG, and then we have this. I guess this is done. Around composite literal 103. Why do we require literals to be? Okay. Okay, we do have to make it a range. We have to range over this. Of course. I forgot a bit of Golang, but yes, it works now and it works nicely. But we don't have anything as request payload, so we just go to up. We actually go to GG. We actually go to cons. We do this. We again go to next and we paste this here. We GG this. Okay. And then we also create another type. We create type repeat payload is a struct which contains min, which is int, max, which is int, and a token, which is token. And then I just run this z, and then we do this, and then we do this, bada boom, bada bam, boom, bam. Then of course we'll do this, and of course this is something we have. Okay. So of course this is self-explanatory. We are repeating the last token for minimum of this time and maximum of this time. Good, GG. The other repetition expression has a bit longer code, but the idea is still the same. We look for the closing bracket and we go ahead till that. Nice. And now we just take a fucking slice of it. We split the string. We take a so there's a lot of conversion going on. But after this, I guess the parts is done, and we go on to building the finite state machine. So we'll just go through this, and we'll get back to finite state machines in the next part of the stream, which will come maybe tomorrow. I don't know. Let's see. So we have funk. Uh, Okay, we have func parse repeat, and then we have this with this. Actually, this is this yang and paste. Yep. Okay. Increment position for character after. Okay, now we have this. Now we just proceed until and unless we find a closing bracket. So for ctx dot, we have regex or ctx dot post not equal to this and there is no and of course we do have this, but again we need one more thing, which is this block right over here. So we gang, and then we go paste it here. And otherwise, if it is not a problem, we do ctx of pause plus gg. So we increment it and this until we find the closing bracket. Then we have the start and the ctx position, but then this time it should be just we can mark it as start. Okay, we have the start, now we have the end. Now what do we have is a, what should we name? Okay, so we have limits, which can be, which is, which not can, which is start to ctx dot position. Of course, the last one is excluded, the first one is included, so we don't have to do anything plus minus. Then we have pieces, then we have we don't have pieces, we have bounds. We have bounds equal to strings dot split. We split at comma, so we have limits comma. Of course we need to organize imports, center. Okay, we do have this. Then what do we have? We have, okay, so we have where we declare max and min. So we have min comma max int. Okay, then what do we have? If length of pieces is equal to 1, which makes sense, then the other one is min is equal to this, value is equal to this. Okay, panic. If length of bounds is equal to 1, we just panic. So we do strcon dot a2i. So it is a2i, which is string to integer, character to integer, whatever you want to say. So we have if value error is this, and then we have error if not equal to nil. Okay, we just fucked it up. But yes, not equal to nil. We can do this, and yes, that's why we fucked it up. Do this now. And this. So now If it is not equal to null, then we have error dot error. We can panic error dot error. Okay, and then we have else min is equal to value, max is equal to value. Okay, and then we have else if it is equal to 2 2 2 2 2 2 2 2 2 2 2 2 2. So if there is 2 2 2 2 2 2 2 2 2, else if len of bounds is equal to 2. Okay, so now the bound is equal to 2. Then we have the same shit over here. We just yank it, we just paste it. Yes. And then we have min is equal to that. Ching, ching. Okay. And then we check all this shit right over here. So we just what do we have to do is vi this yank it. Okay, and then we go this, and then this. We paste it here, and then we have if. But then we haven't filled a to I. We have to fill a to I, which is bound 0. So what we can do is we can do gg a to I. We can do ci this, and we have to fill it with. We have to fill it with bounds of 0, bounds of 0. Then we have bounds of 0. Okay, cool. The bounds of 0. The bounds of 0, 0 and 0. But here we require bound of 1. Q back, yeah. If bounds of 1 is equal to this, and do something, else if fuck me, fuck you. Okay, makes sense. What should we do? We do max is equal to repeat infinity. Yes, make it to refer to infinity, and then we do infinity. We replace it with a and x. So now we just take a slice of, so it is a slice, but we take a slice of an array from the start to the end position -1. We take the slice, we parse it. If there is a comma and we have two values, we assign it to min and max. If we only have one value, min and max both are the same thing. And if we have a min value but not a max value, then we repeat it till infinity. Otherwise, it throws. If there is something else, it throws panic. It panics. Else panic, and panic with errors, error dot, okay, errors dot new. We can say repetition undefined, okay, that should have helped. Okay, cool. Okay, then we have last token is equal to again we have to take the last token, and we do all this bullshit with that. And so for that we can actually copy the code we have. Did I close every bracket? I know. Maybe I might have just forgotten. Oh, I've closed every bracket. Okay, okay, so we have to Z top, Z bottom. Why doesn't it jump? Okay, I'll go to top. Next. The fuck? The fuck? Are you fucking kidding me? So if I do this, but VI this works, this doesn't work. The fuck is this? What is this? So if I want to jump now, what I have to do is to say O, then I have to okay, and then I have to do this. What kind of nonsense is this? So okay, now so we around this. V A O and then yeah, we yank it and then we go to this, we like that and then caps lock, paste it here. Yes, and this works. Okay, so now this all makes sense. Now we have to build the state machine. So we completed the parsing today. Thanks for watching the stream. And yeah, it feels I'm copying the blocks. Hopefully, maybe I'm learning something. I don't know. I'm trying to learn here. And the only thing which I know right now is that I don't like DSA without any specific thing I want to build which will actually help me. So this helps me learning how Regex works. So today I actually took an interest in learning Regex. Initially I used to dread it and I just used to use that asterisk everywhere even while grepping. But yeah, hopefully these streams are forcing me into learning stuff. Currently I learned how React works, not like very in depth, but yeah, by building it from scratch, at least the basic version uh, taught me how different rendering stages are there, what is a virtual DOM, what is difference between rendering it, committing it, or just having it rendered in memory, how certain processes can block the main thread of browser, how can we avoid it, how can we ask browser to run our code when it is free, unlike blocking the complete main thread. So yes, I did learn few things, but yeah, if you say about data structures, so like we built a tree in React. I'm quite not interested in doing that in from the perspective of DSA, just problem solving. But now I'm realizing it is very helpful. Like we did DFS and React, and now we will be making finite state machines. But even if we are not just talking about finite state machines, creating a parser for regex actually involved a lot of string manipulation. Of course, it teaches let's hope it teaches me something about context and what everything is going on here, how parsers work. But yeah, I think they will help me in long term. Let's see, even I don't know. And if they don't help me, uh, anyways, I'll then drop streaming and then I'll do DSA. That is the better option. So yeah, thanks a lot for watching, and hopefully I'll continue streaming videos.